I'm going to talk about a couple of different notions that we could use to make sense of what we mean about the idea for what it means to say that a sequence converges to some point. And so we're going to start by considering a sequence of points just in Rn, so vectors of length n. There's a couple different ways you might approach this. So the first one would be to say that for each coordinate, so j here, j is going to be the jth, so j is going to enumerate the coordinates of a given uk. And so we'll say that the jth coordinate of uk tends to the jth coordinate of u. All right, and so maybe in symbolic notation, I could say something like, let's use this notation right here to indicate the jth coordinate of a vector. So we'll say the jth coordinate of uk minus u is going to tend to 0 as k gets large. This is also as k gets large. Okay, so what does that mean? Well, let's see. So we're looking now at a sequence of vectors, so something that is converging to some point in Rn or something like that. Yeah. So let me draw some coordinate axes and make the picture a little bit prettier here. We'll just do it in R2. That ought to be good enough. So we'll take some point here. This is going to be our u. And if we want to determine whether or not some sequence is converging to it, let's first pick our coordinate 1, j equals 1. And now I want to know if there comes a point, so this is by definition of convergence of limits, if there's some point after which all the terms of the series are within this distance, or have coordinate within this distance of this particular point. So that means that we need it to be the case that all the terms in the tail of the sequence after some point lie in this band, right? And then if we dial up the accuracy factor on the approximation, there has to come some other point in the sequence, presumably later on, so that the entire tail of the sequence lies within this smaller band like this, and so on and so forth, so that in terms of the first coordinate of uk is getting closer and closer to the first coordinate of u. All right, and we verify that works. And we say, okay, so we're good on the first coordinate. Okay, then we go and say, okay, so what about the second coordinate? So now we look at the second coordinate. We say, okay, well, we want it to be the case that eventually the tail of the sequence, all those terms in the sequence, have second coordinate, which is somewhere in this band right here, right? So that the accuracy is that good, and so that means that the term of the sequence has to lie somewhere in this strip right here. And then we make it more restrictive and say, okay, then okay, now I want it to be the case that everything is only within this smaller approximation, which means that the entire tail of the sequence has to lie within this narrower band after some point, and so on and so forth. And the question is, can I always ensure that the tail has of these sequence of coordinates is within there? Okay, so this is what we would refer to as coordinate-wise convergence, or point-wise, because we're just looking at one coordinate at a time, or one point at a time. We fix j equals 1 and then do our whole check on the convergence question based on that. So now let's look at some other So that's one notion. That's one way to describe what it means for the UKs to converge to U. Here's another way. We could say, well, let's just look at the distance between UK and U. And so, as we saw before, the distance is the norm of the difference, right? And so for us, this distance here, this means that we're looking at the sum, and we look at the coordinate difference between UK and U, and we look at the jth coordinate difference, and we take all those differences and we square them and sum them up, and then we take the square root, right? And we say, okay, so that is the standard Euclidean distance between UK and U. Does the distance between UK and U go to 0? All right, and so this means in terms of like tolerance pictures, what we're doing is we're saying, okay, so we've got now, so here's our point U, and we want to know if after some point in the sequence, all of the terms of the sequence lie within this ball right here. So everything has to be in here eventually. And so then that's one choice of tolerance, or one choice of epsilon, to use the jargon. And then we might say, okay, so then if we, but now I want it to be the case that I can approximate to within, some smaller distance. Can I eventually ensure that everything is within this smaller set in here? And so on and so forth, because these are the set of points that are within distance epsilon of U, and so on and so forth. So can I ensure that UK is within epsilon distance of U for all the terms after some point in the sequence? Okay. Then I can also, so that's another definition, and this is referred to as mean square convergence, or convergence in L2, or convergence in metric or distance. And then there's a third way. And the third thing would be to say, let's look at the maximum coordinate difference. So we'll look at the maximum difference in the between the jth coordinate of UK and the jth coordinate of U, right? Does that maximal coordinate difference tend to 0 as we take terms further and further out in the sequence? In terms of tolerances, that means that let's see, so if this is the point U that our sequence is purportedly converging towards, then let's see, so for some tolerance, we say, okay, so we need the jth coordinate to be within such and such a distance, but also the first coordinate, but also the second coordinate, and so on and so forth. So that means that actually everything has to be inside this box. This green box right here, this is the set of all points whose first and second coordinate are each separately, but at the same time, within some given epsilon of U. And then I could again dial up the requirement that they be that all coordinates be even closer to the coordinates of U. And where's my blue? There we go. And that would put everything inside this smaller blue box, and so on and so forth, right? And so we have 3 different pictures. But it turns out that if your sequence of vectors is in any finite dimensional space Rn, so n is finite here, right? Then these are equivalent definitions. Oh, and I forgot to say this last one is called uniform or sometimes supernorm convergence. And so if we're in Rn, all three of these are equivalent. So in other words, UK tends to U pointwise if and only if it tends to U in L2, if and only if it tends to U uniformly. So no matter which one you use, like if you've got a sequence that converges one way, it converges with respect to the other three definitions. And if it does not converge with respect to one of these definitions, it will not converge with respect to the other ones as well. So you might say, why do we care about these different notions of convergence? Well, the answer is that if you have a sequence of functions, so now let's take real valued functions on the interval from minus pi to pi. The standard symbol for that is this one. So that means that each UK is a function from this interval taking real values. These are all different. So it's possible to have a sequence that converges pointwise but not uniformly, or converges in L2 but not uniformly, or converges uniformly but not in L2. Turns out that anything that converges uniformly will definitely converge coordinate-wise or point-wise. But that's the only thing you can say in general about implications between these, and that's not an if and only if. That's only a one-way difference. So that means that the language suddenly just got a little persnickety. So from now on, to say UK converges to U has no meaning. Not if we're talking about functions. You have to specify the mode of convergence, or the type of convergence, or the topology of convergence, whatever you want to call it, the way in which it converges. Does it converge pointwise, in L2, or uniformly? Because different questions have different answers.